Okay, welcome to Thursday. We're going to continue in this week 5 lecture material. We looked at regular expressions on Tuesday. Does anybody have any questions about the regular expression stuff before we press on? Okay. So the next thing we're going to take a look at, and this is going to be quick and very surface level. I want to just demonstrate for you that there are functions provided by the data frame class within Pandas and by Pandas itself for reading data from files into data frames, or for taking the contents of a data frame and writing that out into a file in various different formats. To illustrate this, I have already done the steps on slide 12, which repeats something that we did previously. I have imported my NumPy module as NP. I've imported Pandas as PD. Then I have set the NumPy random seed to 1 to make sure I get the same random values that are shown in the notes, and generated a 3x3 array of draws from a standard normal distribution, mean 0, variance 1. And then down here, now up here I actually misspelled the name of the thing, so I had to redo it to correct the name. And then I created a data frame called F5, which we used previously. It just has these very simple row labels, R0, R1, R2, and very simple column headers, C0, C1, C2, and it's just a 3x3 table of numbers. All right? So, taking a data frame and writing that data frame out to the disk into a comma-separated value text file is very easy. The data frame class has a method called toCSV that you can use for this purpose. So all I have to say is f5.toCSV. And you'll notice here on my screen that there's a lot of keyword arguments that I can use with toCSV, but I'm going to settle for defaults right now, and I'm just going to name this file f5.csv, I guess. Okay, so I'm using the toCSV method to write the contents of the F5 data frame into a text file named f5.csv. And there I've done it. I didn't get an error message, so presumably it worked. And in fact, this is a Linux-like terminal emulator that I have running on my Windows machine, and here I can see, yes, I do have a file named f5.csv. In fact, it was just created at 5 minutes after 3. And if I look at that, I see that it does contain a representation of that data frame. The first row of the CSV file has the column names. Subsequent rows have the row labels in the leftmost column, followed by the values in the data frame. Okay? So if I were to double-click on the icon for this file, it would get pulled into Excel with no problem. All right, so to read back a CSV file and create a data frame from a CSV file, you use the read CSV function. Now, I want to differentiate between toCSV versus read CSV, notice that in the case of toCSV, I have an existing data frame object, and I'm invoking the toCSV method on that object and specifying a file name as an argument to that method. But in the read CSV case, I don't have a data frame yet. I want to construct a data frame from the contents of the file. And so for read CSV, I'm actually invoking this directly from the PD, the pandas module, okay? And assuming that the pandas module's read CSV method works, I will get a data frame created, and I'm calling that data frame F5 copy. So let's see if that works. F5 copy gets pd.read CSV f5.csv. Okay, and it sort of worked, I guess. I didn't get an error anyway. But if I display the data frame, I see that it's not exactly the same as what I wrote out into the file, because read CSV doesn't take for granted that the leftmost column in the CSV file should be treated as row labels. So what read CSV does is to give you these default row labels of 0, 1, and 2, and to treat the R0 as data in the initial column. So the read CSV function by default assumes that this is a file of 4 columns of data. It creates a default column name of 0 for the initial column, and then uses the 3 column labels that I gave, C0, C1, and C2 for the others. And the row labels are created as 0, 1, and 2. Obviously, that's not what I had in mind. So what we can do with read CSV is to use one of its many keyword parameters, index call in this case, and we'll tell read CSV to treat column 0, that is the leftmost column in the comma-separated value file, as the column that describes the row labels. So let me try the read CSV again. F5 copy gets pd.read CSV. F5.csv is the file, and I want the column 0 to be treated as the column that has the row labels in it. And now I get exactly what I wrote out. Okay? All right, so it is, relatively speaking, easy to save a data frame into a file, in this case a comma-separated value file. It's also easy to read that file back in, but you typically do have to learn some keyword arguments to get the behavior to match up the way that you want. And if you take a look at the help messages I'm getting for these functions, f5.toCSV, you'll see that there's a ton of keyword options, keyword parameters in here that I can use to modify how the CSV file gets stored. And the read CSV file is even more either flexible or annoying, depending on your point of view. It's got like 50 different options, 50 different keyword parameters that you can specify to describe how you want that comma-separated value file to be read in. So Google is your pal here, and the official documentation will tell you what all of these various keyword parameters do. Okay, so that's one pair of functions for writing a data frame to a file and then reading a data frame from a file, in these cases in comma-separated value form. Now, just as a couple of other illustrations that I'm not going to type in, here we have a comma-separated value file on disk that doesn't have any row labels. In this case, you will get row labels 0, 1, and so forth assigned by default. And so if that's what you want, that's fine. That's the default behavior. In this file here, f7.csv, we have the opposite thing going on. In f7.csv, we do have row labels for each one of the data rows, but we don't have any column names at all. So in this case, we will use index col equals 0, like we did up above, to tell pandas that the first column here is row labels. And we're also going to specify our own column names using the names keyword parameter. Okay, and then a list of names. Trust me, it works. Okay, and you can try all kinds of other experiments with all the various keyword parameters for this readscsv and toCSV functions. Yes.
So besides those two, the two keywords you showed us, what are the other keywords that you normally use on your database?
I'm sorry?
Are there any other keywords that you normally use?
For comma-separated value files, no. I mean, that's now, okay, so that's a good question. Are there any others that you normally use? I have a general answer to that kind of question, which is you want to try to store data whenever you can in a format that's very easy to read back. So that, so by being careful to store the data in a default format, that makes it easy to read back, and you just have to use the index call keyword. Now, if you get data, from some other source, and you don't have any control over how that data looks, then you may have to do all kinds of wrestling with, maybe it's not a comma-separated value file, maybe it's a semicolon-separated value file, and then there's an option that you have to use to specify what the field delimiter is. Maybe maybe it was created on a Windows system, and you have it on a Unix system, and so now in your Unix system you've got all these stray carriage returns at the ends of the lines. Do you understand what I'm talking about there? If you move data back and forth between Windows and Unix/Linux/Mac, in Windows every line of text ends with 2 characters, a carriage return and a line feed. But in Unix/Linux/Mac systems, every line of text just ends with a single new line character. And so if you create a file on a Windows machine and move it to a Unix machine, you may discover that there's all these mysterious control M's at the end of all the lines on your text. And so you may have to find some option that will say, no, this is a DOS file, or probably nobody even knows what DOS is anymore. DOS is what Windows used to be before there were Windows. So yeah. So on the input side, you typically have to just wrestle with finding options that will work. But I never... all right, so I use the word never, which I try never to do. I typically don't try to memorize lots of options from input or output functions, because it's usually not worth the, it's not usually not worth the brain cells. It's just if you come to a file that's difficult, then you wrestle with the options. And as soon as you've got it figured out, you forget all those options again. Okay? So we can read and write data in comma-separated value files. It turns out we can also, in pandas, if the HTML source code is perfectly formatted, there's a function we can use called read HTML that will scan through an HTML document where you specify the online location of that, the URL for that thing, and the read HTML function will automatically pick out all of the tables that exist within that document. Now, this requires the HTML in the document to be perfectly formatted. If there's anything incorrect about the HTML, then read HTML may fail miserably, which is why previously when we looked at this interest rate table, we used Beautiful Soup, because Beautiful Soup, although it's a pain to use, is a lot more robust and doesn't collapse so badly if there are glitches in the HTML format. By the way, this is a typo at the top of this slide. Up here I claim that pd.readTable reads the tables. The name of that function should be read HTML, as the example shows. So let me actually run this guy. All right, so I'm going to get a list of all the tables from this interest rate website. And apparently it worked. At least I didn't get any error messages. And there are 8 tables, which I dimly remember is the correct number of tables from that web page. Now, if I want to select just the certain web page that had the actual interest rate table in it, you may or may not remember that thing was called the T-chart table. Actually, you probably remember this really well, don't you? Since you just did a bunch of plots involving this data. All right, so I can say I really only want the ones that are labeled T-chart, and I want to treat the first row as headers and the first column as indexes, and this is really slick. It just builds a recognizable table for you without having to do all that fighting with Beautiful Soup. So let me do this. So this is really unfair, because now that you've done all that hard stuff with Beautiful Soup, I'm showing you how you could have avoided it completely. So this is my oh, okay. I didn't think the name of the file made any sense here. I wanted rates df list. It doesn't matter. So let me just display SBDF here, and what it contains. Wait, oh, no. Wrong example. Totally wrong example. I jumped ahead about 5 slides here. I jumped ahead about 5 slides by accident. Sorry, let me try this again. So I want to get just one table from this table list. So what I want to get is the one where attributes is equal to T-chart. And the header is row 0. And the index column with the column labels, or with the row labels, is column 0. Oh, I guess it's supposed to be adders with an S. You know, you should have been in my 1030 class. It worked great then. There we go. There we go. So now, if I look at the first item in this table list, it is the interest rate table that I wanted. There we go. Okay, and you can see that the first row in the table has been grabbed and treated as column labels. So I've got a 1-month column and a 2-month column and a 3-month column. And column 0, which is all the days of these for these interest rates, is used as the row labels. Okay. All right, so we can read and write comma-separated value files. We can read in HTML documents and generate tables, extract the tables from them, assuming that the HTML is properly structured. You can also take a data frame and write it out to a file that's an HTML file. A third kind of data format that's very popular in the web is JSON, the JavaScript object notation. And it looks vaguely Pythonish. In fact, it's a very tidy, very simple format. And you can learn everything you possibly want to know about it in about half an hour looking at the json.org webpage. JSON format looks sort of vaguely Pythonish. Here I have my F5 data frame. And if I say f5.to JSON and specify f5.json as my name for the file, all right, there's the f5.json file that I just created. And basically, in JSON, the way this data frame is represented is I have a JSON object. Here. Too many screens. I have a JSON object which is contained within these outer parentheses, and within that JSON object I have a sequence of what looks like dictionaries. The column name is effectively like mapped to the sequence of row values for that column. So I've got in column 0, row 0 is 1.624, row 1 is minus 1.073, etc. And then for column 1, I've got similar kind of information. So it's a little less compact than a comma-separated value file, but it turns out to be a very rapid kind of format to parse, and it's able to describe data that's more complicated than just mere rows and columns. Okay, so you may have found, as you cruise around looking for data sources for your project, often websites will provide a JSON API that allows you to download data sets that are in JSON format. And you can then parse those pretty easily. I'm going to show you a silly example that I found. Way back when I first developed this course, I was teaching it for the folks in Adelaide, Australia, and I thought, well, I should try to use some of their data, and I discovered, to my delight, that Australia has a really well-organized repository for government data at all levels, national, are the regions in Australia called states? I've forgotten. Somebody must know that. What is New South Wales? Is that a state or a province or I'm sorry? A state. Okay. Yeah, so it's got by national and state and regional and city data in there. So if I say data.gov.au, I get this terrific interface that I can just type stuff to. And when I first started exploring this, one of the very first things I found that caught my attention was Wyndham Smart bins. And I thought, what in the world is a Wyndham Smart bin? Well, it turns out that Wyndham is a city not too far from Adelaide, I believe. And the garbage bins that they have that are managed by the city are not mere rectangular blue or green boxes like we have around here. These things have sensors in them, and they know how full they are. And you can use a JSON query to find out how full the smart bins in Wyndham are. Okay, so here we go. Here's the Wyndham Smart Bin fill levels, and I'm provided with a JSON interface. In my code, I can actually include this URL to get the JSON representation of the current fill levels of the bins. Okay, so that was the example that I mistakenly showed you earlier. Let me show it to you for real here. So here is our URL describing Wyndham's smart bins. So this is my smart bin data frame, SBDF, and there are apparently 68 lines in here. And here we are. Okay, so they're just numbered as far as the rows go. So row 0, row 1, etc. And if I break that out by using some formatting features, what I end up getting is, for each smart bin, I have the exact latitude and longitude where that thing is located. And then I have a whole bunch of properties of the smart bin, including how full it needs to get before it's considered to be full, and what its current fill level is. As long as the current fill level is less than the threshold, then the status here is going to show as not ready. But when that bin fills up, here we have a bin that has a maximum threshold of 8, and it's actually at 8. The status changes to fullness. This data is updated more or less in real time. So each time I go out and download this data, it's telling me the current status of these bins. And so I, as a city employee, could very easily write a little program that analyzes this data every 15 minutes or so, and notifies whoever is driving the trash pickup truck. Oh, at this bank over here, there's a bin that needs to be emptied. Okay, so that's I will grant you that smart trash bins is maybe a little bit of a silly example, but on the other hand, it's really pretty cool. This data is just out there. If you have JSON a JSON API to get it, you can download it. You can pick it apart inside of a JSON data inside of a pandas data frame. And write whatever programs you want to deal with that data. Okay, so that's just kind of a quick overview of some of the facilities that are available for interacting with comma-separated value files, HTML documents, JSON documents, and there are other facilities available for handling other formats. Yeah? Can we, I'm sorry?
Upload a local text file via pandas to Python.
Now, is the text file formatted in some way, or?
Yeah. Like, what if it's a list of lists? Or maybe it's a table or something.
Okay, so we have been working with, you folks have been doing stuff with the expenses.txt file, correct? And so that's just a regular text file. It does not have, it's not a comma-separated value file because the descriptions have commas in them, so we had to use colons instead of commas. And we saw that if you just have a text file that doesn't match some predefined, well-known format, you can just pick it apart using split and lists and loops and so forth. And you don't need pandas for that. You can just you can just get in and do it yourself. Now, it is true, though, again, to pick that particular example, that one of the keyword options you can use in the read CSV function allows you to alter the delimiter. Now, I'm very curious. Do I have? I don't have that file here. Let's see.
Can you try with daily codes?
Sorry?
Daily codes? Can you try with that? If you have that.
I'm sorry. I got this fan over my head. I can't quite hear you.
Can you try with the daily yield codes that you did in our homework if you have that?
With the daily yield curves, okay, so you created a file containing that information.
Yeah, a list of lists.
I'm not sure I actually have that
No, that's
myself. Let me though grab a copy of the expenses file. Okay, so this thing is a colon-separated value file. It's formatted, but it's not in a format that is widely used. And I should be able to say into a data frame, let's say DFE, let's pd.read CSV expenses.txt, but using as a separator the colon character instead. And so the first row will be columns, so that's fine. Yeah, I think this should work fine. There we go. Okay, so since this file was formatted in some kind of reasonable way, and I was able to read it as a CSV file except with colons instead, I got these default row labels of 0, 1, 2, 3, 4 and so forth, but that's probably fine. Other questions? Okay, so in this last part, we're going to take a look at a variety of string handling methods and functions. We know various ways of manipulating strings already. For example, we know that if you have two strings and you stick a plus sign between them, that concatenates the two strings together. If you have a string and you use the asterisk on a number, that means you want to repeatedly concatenate that string together with itself. You can subscript within a string to get an individual character or to get a slice by using the colon. And we've also, I'm not sure I mentioned it in class, but I know that in a homework you needed to split some text. So let me we'll get to an example of splitting shortly. So this is a lot of what we already know, but it turns out that there are a ton of additional things that you can do with strings, and you can look at the official documentation to see this long list of string manipulating functions. I'm going to describe many of these sort of chunked up into categories rather than, in the documentation they're just alphabetical, but I'm going to talk about them sort of in categories. There are several functions that allow you to modify the case of letters in strings. So if I have the string, come here now, mouse. There we go. So if I say s gets, this is a test, then I can invoke the capitalize method on s to get back a copy of s with the first letter capitalized. Yay! Now, that doesn't change s itself, that just changes the copy of s that I get back, in that the first letter has been changed to a capital letter. Another method, which is a little odd, I wonder how often people actually use this one. If I say s.title, what I get back is a copy of s in which the first word of each, the first character of each word has been translated to uppercase. I can say that I want to convert all of the characters to uppercase by saying s.upper. And if I have a string of mixed case letters, let's say s1 is, this is some text with mixed case. If I say s1.lower, then all of the uppercase letters get converted to lowercase. Notice that for both upper and lower, and for that matter for capitalize, the spaces just get left alone. The spaces just come through as spaces. So far, so good? Okay. We can also do left justification, right justification, and centering of strings using some methods. Here I have s just being 4 characters wide, word. And if I say s.center and specify a width of 10, what I'm going to get out is a 10-character wide string in which the 4 characters in Word are centered. So it's going to be 3 spaces, that's the default fill character, and then Word, and then 3 more spaces. Okay? If I don't want spaces for my fill characters, I can specify a different fill character. Maybe I want dots instead of spaces around Word. Okay, so now I have 3 dots, Word, and 3 dots again. Good. And I can also do left and right justification. With ljust and rjust. So s is still Word. If I say s.ljust in a field that's 10 characters wide, then Word comes out on the left side and it's followed by 6 spaces. Or s.rjust in a 10-character wide field. Now I've got 6 spaces followed by Word. And here again, I can specify a fill character, so s.rjust 10 with a, let's say, a plus sign. All right, so those 3 functions give you a lot of control over the justification of your string and also what fill characters you want on either side of the string. The strip function and its relations, lstrip and rstrip, allow you to eliminate whitespace characters, so-called whitespace characters, either at the beginning or the end of a string, or both. Let me set s equal to 3 spaces followed by WRD followed by 3 more spaces. Then I believe that you've seen this already, but if I say s.strip with no argument, the space characters at both the beginning and the end get peeled off. Now again, that doesn't directly change s, but it does change the copy of s that I see. If I say s.rstrip, that only strips off the spaces at the end, and if I say s.lstrip, that only strips off the spaces at the beginning. Okay? Now, I've said that these functions are stripping off white space. Not only spaces count as white space. White space also includes things like newline characters, carriage return characters, horizontal tab characters, and other more obscure characters that nowadays people don't really use. Believe it or not, there used to be something called a vertical tab on an old-fashioned paper computer terminal, and a form feed, which would automatically feed the rest of the page out and get you to the next page. All of these things are classified as white space. So if I have an S, let me create S1 that has a bunch of different kinds of white space in it, like a few spaces, horizontal tab, new line, more spaces, carriage return, form feed. I guess I get clumsy in the afternoon. And then we have Word, tabs, new lines, carriage returns, form feeds, spaces. Okay, so this, oh goodness. I've got some kind of magical character in there that I don't want. Oh, maybe that's a form feed. Interesting. Cool! So the form feed has come out on my screen as this up arrow symbol. If this were a paper terminal, it would have kicked out the page and loaded a new page. In any case, all of that stuff is white space. And so if I say s1.strip, it all goes away. Now, I do want to offer a warning about these strip functions, which is that very often when people are using these strip functions, they're actually stripping more than they intend. If you are reading data from a file, from a text file, you know from examples that we've done that the input line is going to end with a new line character at the end. And you usually do want to throw away that new line character so that you just have everything up to but not including the new line character left. But what if you have a line of input from a text file that looks like this is some important information, 12.345 space. Now, if you say to strip that, then all of the spaces after the 12.345 are removed. And frequently you don't want to do that. So that's why I suggest, if you really just want to get rid of the very last character, then don't use an rstrip. Use instead the slice up to but not including the last character. Okay, and so that will leave all of the characters in the line except for the very last character. It's safer and more consistent than using rstrip. Make sense? Okay. All right. So let's see. So we've looked at tinkering around with letter case. We've looked at justification, left, right, and center. We've looked at stripping. Now we're going to take a look at several functions that are available for testing the characteristics of a string. Let me create s equal to word, s2 equal to some digits, s3 equal to catch 22, s4 equal to stop, okay, so now I have a collection of strings s, s2, s3, s4 that I can use to demonstrate some of these string attribute testing functions. I can ask whether s dot is lowercase, and I get back a true. Or I can ask whether s is is alphabetic, and I get told that's true. If I ask whether s2 is lowercase, there are not any letters in there, so nothing in there is lowercase. If I ask whether it is alpha, it's definitely not. But if I ask whether it is numeric, I get told yes, it is numeric. Now there's also an isAlNum function that tests whether something is alphanumeric, meaning some combination of letters and digits. All right, so S2 is alphanumeric. S is also alphanumeric. But S is not numeric. Good. So I can test whether something is lowercase, I can test whether something is uppercase, whether it's alphabetic, whether it's alphanumeric. There's even a test that I can use to determine whether a particular string satisfies the requirements for a Python identifier. A Python identifier, which is a name you could use for a variable or a function or a class, we know has to start with a letter or a digit or has to start with a letter or an underscore. And then following that can be any number of additional letters, digits, or underscores. All right, so if I test is identifier on this string root 66, I'm going to get told that that's true. So root 66 is a valid identifier. 23 skidoo, on the other hand, is not, because the first character is a digit, not a letter or an underscore. Anybody in here recognize 23 skidoo? Heck no. So 23 skidoo, about 110 years ago, was like the most popular slang word in American English. And what it meant was, let's get out of this joint. Why? Who knows? But you can look it up on Wikipedia and you'll learn all about the history and origin of 23 skidoo. It was just the first thing that came into my head that started with digits. There's no importance to it other than that. Okay. I can also ask whether some string is all white space. Okay, is space will give me back true or false. Now, we previously talked about the split command, or the split function. If I have s referring to this is a test, and I say s.split, the split function will split a string into a list of substrings. And by default, the split function will do that at space characters. So s has 4 words in it, separated with 3 spaces. If I split s, I end up with a list of 4 strings, like so. Now, the opposite of split is join. If you have a list of strings, how could you get those merged together into a single string? And, okay, so I tell you, well, you can use join. And the obvious thing that people try is to say, okay, m.join, and let's use a space to join up these strings in M. Seem plausible? Unfortunately, that doesn't work, because joining is not something that a list knows how to do. Joining is something that a string knows how to do. So weirdly, you sort of have to flip the order of these two objects, M and the space, and what you do instead is you say space dot join M. Okay, so join is a method available for the string, and the string is treated as the character around which the components in M, the items in M, should be joined. And so that's how I get back my original string, this is a test. You can use any join string that you want. So I could use, let's say, 3 spaces as a join string, and join M, and now I'm going to get 3 spaces between each of the words. Or I could say plus minus plus minus plus dot join, whoops, I'm quote in the wrong place, dot join M. Or if you wanted to eliminate all the spaces, you can use an empty string. Okay, just type quote quote dot join M. And now the strings in M all get joined together with nothing in between them. Everybody good with join? All right. I can count how many times a certain string occurs in some other string. So this is a test, and if I say s.count space, I get told there are 3 spaces in there. If I say s.count a, okay, there's only one a. Count little t, there's 3 t's. There's no restriction on the pattern being a single character. I can search for s space, let's say. All right, there's 2 occurrences of s space. We've got s space right there, and then later we've got s space right there. So that's counting. You can also search a string to see whether it does or doesn't contain a certain substring. All right, so here's my string s, and if I say s.find and specify a little t as the substring I want to search for, the find function will start from, by default, the beginning of the string and report back to me the index of the first little t that is discovered. All right, so this is a test, s.find of t returns to me a 0 because there's a t right at the very first character. As a second argument to the find function, you can specify the index where you want to start searching. So, since I was told that there was a t at index 0, I can do my next find to say, all right, let's look for t again, but this time let's start at index 1. So that's going to skip over the t at index 0. And find will keep looking for a t until eventually it finds the next t, which turns out to be at subscript 10. And I can keep going by saying, okay, let's start at position 11, see if there's any t's following position 11. And there is. All right, that's good. Let's see if there's another t starting after that t. We'll look at position 14. Now, here I got a -1. Because -1 is what the find function returns if it cannot find a match for the string you've told it to look for. And that makes sense because the length of this string s is only 14. I mean, there are only 14 characters in this string. Therefore, the indexes go from 0 up to 13. And, you know, there can't be any characters starting at position 14. So I'm going to get a -1 back from find. Let me do a little more blazingly obvious example. If I say s.find capital X, well, clearly there's no capital X's in this is a test. So when I hit enter, likewise I get back a -1. So -1 is how find tells you that it could not locate the substring that you asked it to find. These examples, the little t and the x, were one-character substrings, but of course you can look for multi-character substrings. So if I say s.find es, all right, there's apparently an es starting at position sub 11. That makes sense. This t was at position sub 10. So here we have an es starting at position sub 11. Our find simply starts at the end of the string and works backwards rather than starting at the beginning and working forward. So if s contains, this is a test, and I say s.rfind a t, Well, we know that the last t was at position sub 13, so I should get that same value back. Yes, so I get told that the last t in this test is at offset 13, or subscript 13. Everybody cool with find and rfind? Okay, now within a string you can replace one substring with another by specifying the original string that you want to search for as the first argument to replace, and the new string that you want to replace that original string with as the second argument. All right, so here's my function, or my my string s, and if I say s dot replace substring little t with substring capital T, this replace is going to happen throughout the string. So each little t gets replaced with a capital T. Very often that is what you want, is for every occurrence to be replaced. But if you only want, let's say, the first one to be replaced, then you can specify as an additional argument how many occurrences you want to have replaced. So if I say 1, then only the first little t gets replaced with a capital T and the other ones are untouched. Good. You can also use an empty string as the replacement string if you want to simply clip out characters entirely. So here's my string s, and if I say s dot replace, well, let's replace each little t with nothing at all. So each little t is going to get replaced with nothing, and I have his is s as my result. Now, either the first string or the second string in the arguments to replace can be multiple characters rather than just one, and that'll work. Everybody good with replace? All right, so the last thing I want to talk about as far as formatting is the format function. A little bit of background here. Since Python is an open source project, and everybody has their own ideas about what the simplest and most convenient way is to format output properly, it turns out if you look through the documentation for Python 3.7, there are 4 different families of facilities that you can use for formatting strings. Now, I personally think that if a language has 4 different ways of doing something, it probably has 3 too many ways of doing that thing. And so I strongly suggest that, and you may not choose my favorite, but choose one method for formatting and learn that one really, really well, and just forget about the other 3. Okay? Now, the format function is very heavily based on the C language's printf function, which prints formatted information. And it uses format codes, so-called, that are very similar to those from printf. It's likely that in other languages you'll also encounter similar kinds of format codes. So this is a style of notation that you can learn once and apply in a variety of different languages. It's not exactly the same in Python as it is in C or other languages, but it's really close, and so this is the one I'm going to concentrate on. What about formatting output? Well, if you work for somebody, they want you to format output neatly. Trust me, they do. And if columns are supposed to line up neatly, and if columns are supposed to be a certain width, and if the justification is supposed to be left or the justification is supposed to be right, you need to be able to know how to do all of that stuff. So here I have an example in which I've specified a format string that's using two format codes, a D, which means decimal or base 10 integer, and an F, which means a fixed point representation of a floating point number. And given that format string, I've called the dot format method, and I've specified an integer as the first argument and a float as the second argument. Okay, so whoops, too much yellow. There we go. So let's try this out. I'm going to say ask gets, okay, my first format code. Now, a format code, for our purposes, is going to start with a curly brace and a colon. You can get fancier than that, but there's no need to be fancier. So a curly brace and a colon, that's going to be our first format code. The less than symbol means that we want left justified output. The 6 is the field width for the output, and the D means that I want to display a decimal that is a base 10 integer value. Okay, so my format specification begins with an open curly brace and a colon, and ends with a closing curly brace. After that, I have a comma, and the comma is just a literal character. The comma is just representing a comma. Now I have another format specification, so I start with curly brace colon. This time I want a right justified 7-character wide field. Dot 4 means I want a precision after the decimal point of exactly 4 characters. And F here means fixed point, which is to say there has to be a decimal point displayed, but there must not be an exponent displayed. All right, so that is my format specification. And now when I say dot format 1234 and 7/3. All right, so this number 1234 is an int, and it's going to be formatted in place of this first format specification into a field that's 6 characters wide but left justified. That means that it's going to come out looking like 1, 2, 3, 4 space space. So those are my 6 characters. 1, 2, 3, 4 space space. Then I'm going to have a literal comma. 7/3 is 2 1/3. So it's 2.33333 and 3 forever. But I've told the format specification here that I only want to see 4 digits after the decimal point, and I want the field to be a total of 7 characters wide. All right, so in that 7 characters, the decimal point counts, the 4 characters after the decimal point count, so that's 5, and then any digits that exist in front of the decimal point also count. In our case, we know that in front of the decimal point we're going to have a 2. So we've got, let's see, so we've got, what is that, 6? We've got 2.3333, 2 thumbs. Right justified. So here is the result. Here's a 6-character wide field containing that base 10 integer representation, and here is a 7-character wide field with 4 digits after the decimal point representing 7/3. And then, of course, here is my literal comma in between those. Okay, so that's a sample, and now I just want to build up the pieces of this in a little more detail. Any questions so far? Okay, so as a general thing, if you want to use this .format function, you have to specify a format string and then say .format, because the format function is a method that operates on a format string. And then for each format code that you have in your format string, you have to have a corresponding value as an argument to the format function, and that value has to be of the correct type. What do I mean by the value has to be of the correct type? Well, let's do this. If I say format as a decimal number, decimal integer, the value 7/3. Well, 7/3 is a float. It's not an integer. So I just get an error. Oh, well. Actually, I got an error for a totally different reason. I got an error because I typed my format code wrong. It should be open curly brace colon and then a D and then .format 7/3. Okay. And because I chose a format code for integers, but the corresponding argument was a float, I get yelled at. So the example that I showed to begin with, back up here, let me copy and paste this one so we can have it for reference. This example was using D, meaning that we want an integer as a decimal or base 10 representation, and F, meaning that we want floating point values represented in a fixed point format. That is, we want a decimal point, we don't want any exponent. Some other format codes that you can use are S for string or E for an exponential floating point value. That means that you want to see the decimal point and the exponent displayed. And here I have an example illustrating those 4 different format codes. Okay, so I'm displaying a decimal integer. I haven't specified a field width or a justification marker, so the integer is just going to come out in as few characters as it will fit. And the corresponding integer argument is 123. So this value, 123, is going to come out represented in decimal, and it just looks like 123. Then we have a literal comma and a space, and that comes out looking like a comma and a space. Then I have a string. Okay, S for string, and hello comes out in place of that format code for the string. 2 dashes come out as literal characters. Okay, so I get 2 dashes out. Then I have a fixed point representation of 7/3, followed by literal colon space, and then an exponential representation of 7/3. For these 2 floating point format codes, I have not specified either a field width or the number of digits that I want to have after the decimal point. The default that I get for digits after the decimal point is always going to be 6 in that case. All right, so my output, let me copy and paste this thing in. So if I paste that in, here we have my my result. That is the string contained in S. It has 123 as a base 10 integer, then it has a literal comma space, then it has hello as a string, and then a literal pair of dashes, and then this fixed point representation of 7.3 is a 2 followed by a decimal point followed by 6 threes. 6 digits after the decimal point is the default. The exponential output is also 6 digits after the decimal point, but it also includes an exponent as well. So this is 2.333333 times 10 to the 0 power is what that's saying. Okay? Now, just to show you a little variation here, there are other ways that I can display integers. So instead of decimal integer, let me display this as a hexadecimal integer. All right, so 123 in hexadecimal is 7b. Now, does that make any sense? Well, let's see. That's a 7 in the 16s place. So 16 times 7 is 112, or 1... Okay, 16 times 7, 7 plus... Yeah, it's 112. And then, yeah, that makes sense. Yeah, so 112 is for the 7, and then b is 11, so 112 plus 11 is 123. If you're not a hex person, it doesn't matter. You don't need to panic. I just want to show you that you're not forced to represent integers just as base 10 decimal numbers. You can also represent them as base 16 hexadecimal numbers, and some other formats as well. So far, so good? Okay. Now, because this format stuff was inherited from the C language, and the C language does not have the idea of Booleans or a value none, there are not any format codes for representing Boolean values or none. But that's not a problem because you can simply convert none to a string, and you can convert either true or false to either an integer or a string, and then you can just use the equivalent format codes, S for string or D for base 10 integer, and that works fine. You can, as I showed in my original example, specify the width of the output field that you want to see. And furthermore, you can also specify the digits after the decimal point. Now, this example here is displaying... Okay, so k is going from 0 up to 4. And we're displaying k first in a 3-character wide field as a decimal number. So there's a 0 with 2 spaces in front of it there, and a 1 with 2 spaces in front of it. Here I'm displaying that digit having been converted to a string. And strings by default come out left justified instead of right justified. Then I have my fixed point and my exponential notation, which by default I have 6 digits after the decimal point in each place. But I can also specify a dot precision with F or E to change the 6 to some other value. And I already, in the very first example we looked at, showed you the less than symbol for left justifying, the greater than symbol for right justifying, and it turns out that you can use the caret symbol for centering. So, if I do this, I'm starting a format code, and now I'm going to say 8D. That's my first one. And then a space, and then 8S, and then another space, Actually, instead of spaces, which are a little hard to see, let me use vertical bars. The vertical bar is just literally going to be printed. Okay, and then I'm going to say curly brace colon 12.2f, and as another alternative 12.4f, and as another alternative, let's say 25.18f. .123, hello. And now I want 7/3 3 times. 7/3. There we go. Okay, so this is an integer in an 8-character wide field. It is right justified by default. Here's a string in an 8-character wide field. Strings are left justified by default. Here's a fixed point, floating point, 12 characters wide with 2 digits after the decimal. Here's also 12 characters wide with 4 characters after the decimal. And here we have 25 characters wide with 18 characters after the decimal point. And notice that if you ask for 18 characters, you're going to get 18 characters, even though everything after the 13th character is just rounding garbage. So be careful that you don't ask for more precision than actually exists within the value that you're trying to display. All right, so that... okay, so we have gone a couple minutes over. I apologize for that. I just want to impress on you that this stuff is kind of picky, but if you just force yourself to learn this formatting rules one time and memorize it, you'll never have to look this stuff up in a book ever again, and you'll always be able to know how to format stuff in a way that looks nice to your customer or your boss or your colleagues. All right, so that's it, and I'll see you next week.